Good morning. Today, we are talking on dental ceramics. And in dental ceramics, in particular, we'll be discussing strengthening of dental ceramics. And I am Dr. Shyam Mohan, Professor, Department of Prosthodontics, PMS College of Dental Science and Research. Replacement, any artificial replacement should be lifelike. As you can see here, when you replace a natural tooth like this, the artificial materials we use should be real lifelike. So that is where the importance of ceramics come in. So whenever we need a natural replacement or a natural looking replacement for natural teeth, ceramics is the first and the last choice in dentistry. There is no other material to beat the translucency and the lifelike looks of dental ceramics. So where is this term ceramic derived from? It is derived from the word keramos, which means burnt stuff. And as you know, it was first made in the form of earthen pots, and all the civilizations, you can see the Indus Valley civilization, the Mesopotamian civilization, in all these civilizations, all the earthenware things retrieved were basically ceramic only. So they were all clay. So the basic ceramic metal is clay, which we still use. And when the clay is molded into a particular shape, placed in kilns and burnt or heated in kilns in very high temperature, you get baked silicon material, which is the burnt stuff, which is a burnt stuff, and that is ceramos, meaning ceramics. So basically, the first type of ceramic is clay only, with silica and feldspar added to it. But that is for the industrial purpose, for other purposes. But when it came to dentistry, this kaolin is removed and we have just the silica and the feldspar in it. So by definition, ceramic is an inorganic compound with non-metallic properties, and it has got metal and semi-metallic elements also. And the semi-metallic elements are the aluminum. The metal and the semi-metallic elements are, example, aluminum, calcium, sodium, potassium, titanium, lithium, zirconium, and the like. So what are the features of this unique, fantastic, aesthetic material? It is resistant to corrosion. It is resistant to wear. The interesting fact about ceramic is that ceramic is harder than enamel. So rather than enamel causing wear and tear of a dental material or a restoration, it is a reverse that happens with ceramic. Ceramic can cause wear and tear of the enamel. But there are some materials which are softer than enamel, which will not cause attrition of enamel. You will learn about it later on. And this is one of the most color stable dental materials we have. And as I've already mentioned, it is highly aesthetic because of its real lifelike tooth color matching faculties and also being translucent, allowing light to pass through it because it contains glass particles. It has got very low thermal and electrical conductivity. And of course, all these materials are tested in the mouth, and it is really biocompatible. We don't use any dental materials currently used, then not at all toxic to the tissues or the oral environment. All these are biocompatible. And we can mold it into whatever shape you put. Already we started with the primary ceramic material, the clay. And as you know, like clay, it can be molded into any shape. Same with dental ceramics. Any type, whether it is an incisor, it's a molar, or it's a premolar, or whatever shape you want, you can mold this material and get real life-like prosthesis. And being very hard and having such good properties, it is really stable over a long period of time and function very nice in a patient's mouth for a long time. But All these come with disadvantages too. The main disadvantage is that it is very brittle, and the another problem is it is quite costly because we need special equipments and we need personnel with special training to deal with this material. So where are they used for? It is of course used for making prostheses like crowns and fixed partial dentures, and comes in two forms: metal ceramic form and an all ceramic form. Metal ceramic, there will be a metal core inside with the ceramic coated over it. While all ceramic, the core is also ceramic and the coating is also ceramic, or sometimes the whole thing is made of one solid ceramic block, which is called a milled catcan crowns. So basically, we have two types, and all these are used for making crowns, bridges, inlays, onlays, veneers. So the application is same, but it comes in two forms. One is metal reinforced one, the other one is all ceramic one. Metal reinforced one, you have the core with metal with the ceramic veneered over it, while the all ceramic, we have a ceramic core only, no metal in it, with the ceramic coating, or the whole thing can be milled out of a ceramic block. So one of the most popular uses of this is use of making crowns, lifelike looking crowns. So crowns are usually given on single tooth. So usually following root canal treatment or post-sedative, we keep these crowns. Or there are other indications when the tooth is not aesthetic enough or the tooth has got functional problems, we modify it and cover it with a restoration that is called the crown. And ceramic is the best material for crowning because it can be made copying the rest of the teeth in color, texture, look wise, everything, making it very aesthetic choice of restoration. And this is the bridge. So the other one, a crown is given on a single tooth, while bridge is given as a replacement of a lost tooth. So bridge or FPD, fixed partial denture. So it's a partial denture. A partial denture comes when tooth or teeth are missing. So in this picture, you can see one tooth is missing, which is the second molar. Sorry, which is the first molar. The first molar is missing in this picture, and we are given a 3-unit bridge. So the 3-unit bridge, it has got two abutments, and the replacement tooth, the artificial tooth, is known as pontic, which is connected to crowns which are given on the molar and the premolar respectively. And this is luted in place using dental cement. So this is called the FPD, or the fixed partial denture. And both metal ceramic and all ceramic materials are used for making this prosthesis. And these are examples for inlays and onlays. These are made using pure all ceramic without any metal core. So you can see that the first one is an inlay and the other one is the onlay. Inlay will be confined to the occlusal surface of the occlusal will be confined to the occlusal surface and the occlusal table, while an onlay, it covers the cusp tips too. So that's the difference between inlay and onlays, and ceramic is the best material for making both. So ceramics can be classified according to the composition, according to the way it is processed, according to foreign temperature, and based on the crystalline phase and applications. So according to composition, it has got pure alumina, it has zirconia, it has silica glass, lucite-based glass ceramic, lithium-based ceramic. So these are different types. And according to processing, there is something called sintering, then there is casting, there is slip casting, some pressed ceramic, then there is milled catcan ceramic, and recently there are even 3D printed ceramics too. According to fire and temperature, it can be high fusing, it can be medium fusing, low fusing, ultra fusing. And based on the crystalline content of the ceramic, can be classified as aluminous porcelain, feldspar based porcelain, lucite rich porcelain, and spinel based porcelain. And account application can be only for the core, which is called the core porcelain, or it can be the veneer type, which is the enamel porcelain, and something that comes between the core and the enamel, which is called the body porcelain. And basically, majority of ceramics have this structure. It has a glass face and a crystal face, which gives the translucent, glassy, tooth mimicking looks. So this is how the structure looks like in a microscope. So there is the glassy amorphous face. That is a general face in which the crystalline faces, you can see these crystals. In this, these crystalline crystals are dispersed. So that is how it looks under the microscope. And there are different types of ceramics: lucite, fluorepid, silica based. Silica based only different types as a so lucite based, spinel based, zirconia, aluminum, lithium. So many types of ceramics are there, which you will come to know later on in the later sessions. And basically, the ceramics are made up of feldspar and kaolin. Feldspar is the main constituent, and it contains potash, soda, and silica. And that constitutes about almost 85%. Then kaolin, but kaolin is not there in the newer ceramics. Earlier, we used to add kaolin, but it makes the ceramic very opaque. So for the opaque ceramic, we can have the kaolin, while the enamel and dentin ceramics, we cannot have it. So this is added to the up to 5%. It increases the moldability. It acts as a binder. And the only problem is it makes it very opaque. So we can have kaolin only in opaque porcelain, not in other porcelains. Then another major constituent is quartz to the amount of 13 to 14%. It gives strength, firmness, and translucence of porcelain. And this serves as a framework for other ingredients. Then we have the glass modifiers and opacifying agents. Glass modifiers are the potassium, sodium, calcium oxides. They serve as fluxes too. They lower the viscosity of the glass and increase the thermal expansion, while the opacifying agents are zirconia, titanium, and tin oxides. And we have many pigments because the teeth come in various hues, various shades, and usually it falls between the yellow and the yellow red spectrum. So each one has got an individual color to the teeth, isn't it? So to mimic that, we have to add color so that it looks like natural teeth. So metal oxides are used for this, and metal oxides are fused with this glass feldspar, and it is ground into it, and it is applied over also. Okay, basic one color is there, but to fine tune it after making the crown, we can mix it with something called glaze and paint it over it and make it better. So the metal oxides are either present in the basic paste only, or it can be added to the added superficially also to mimic natural tooth color. And what are the common metal oxides used? Iron, nickel oxide, copper oxide, titanium oxide, cobalt oxide. So see the colors. So all these oxides give, if you want slight brownish, a green, you're wondering why you need green. So it's not like green, blue, lavender. We mix these, and when you fire it, you will get the spectrum falling within the yellow and the yellow red. So don't get surprised seeing that why you need a green and a brown and a lavender and a blue. Once mixed and fired, it gives a spectrum falling within the range of the color spectrum for human natural teeth. Then the main constituent is feldspar, which is a silicon dioxide matrix. So feldspar is nothing but silica, which amounts to maximum 65%. Then it has got little bit of alumina amounting to 11 to 20%. Then it has potash and the soda and other additives. So feldspar is a naturally occurring mineral and it is also known as albite. And most of the components needed to make dental processes are present in this. And it can be fused at very high temperature. Then it forms a glass containing material and that gives the translucency to ceramic. And of course, because of that, it is colorless and being glassy, transparent, as already mentioned. So kaolin is a white clay-like material. It acts as a binder. It gives opacity to mass. And some manufacturers use sugar or starch instead of kaolin. Next is quartz. It's a kind of silica. And ground quartz acts as a refractory skeleton. It provides strength and hardness to porcelain during firing. It remains relatively unchanged during and after firing. So this is the way these are all supplied in powder form, and it is supposed to be mixed with a liquid or distilled water. Then it can be molded into any desired form you want, and it comes in enamel, dentine, and opaque powders. So this liquid is either a special liquid or a distilled water, and stains and color modifiers can be mixed to it. And once it is fired, you can take the glaze and add on to the porcelain. And of course, there is a shade guide helping us to exactly match the patient's tooth color to the type of feldspar, type of ceramic powder we're going to work with. So this is how it comes. It comes in different bottles. You can see like each one denotes each tooth shade or tooth color according to which we can take. So usually if it is a Vita shade guide, it comes in A1, A2, A3, A3.5 like that. So the powders are also available in these shades. So once we match with the patient's tooth color, the appropriate ceramic powder is taken. The same shade will be the same shade opaque, dentine and enamel powders will be taken for the work. So these are the ways ceramic restoration is made: by condensation, preheating, sintering, glazing, and cooling. All this will be elaborately dealt with in that particular topic. My topic actually comes to strengthening of ceramics. So I'll be just brushing through it because only once you get this point, I can go to my topic proper. So condensation is technique by this molded ceramic powder paste is applied over the core material and then it is fired. So there are many methods of mixing this powder and condensing it over the core and firing it. So these are different steps and that will be dealt with in another class or already it would have finished by the time you're seeing this video. So these are different methods of doing it. So first you mix the opaque and keep on apply it on the core and fire it. Then you same thing you do with the dentin and then the enamel powders. So a dentin powder and enamel powder. Then all these are, applied over layer by layer and it is first preheated, then it is fully fired in ceramic furnace. So these are various steps of drying it, firing techniques, and different happenings during firing. And finally, once you get the product, you glaze it. So that's a liquid. You take the liquid and you can brush, as you can see in the picture, it is brushed over the final product. And you can add stains to it and make it really lifelike, matching the adjacent tool. So glaze gives the final shine to the crown and also the fine tuning of the color, matching it exactly to the patient's. So these are different ways you do all this. And there's something called auto glaze. You learn all this in the subsequent classes. Or Then there is something called overglaze. Then there is cooling once because it's a hot oven. So it has to cool down. And this will be the assignment once this is dealt with in detail. And you can go to YouTube and watch all these videos. Now, coming to my topic proper, that is strengthening of ceramics. So, why do I have to strengthen the ceramic? That's the first question. So, in spite of the excellent aesthetic quality, only problem with ceramic is that it is having very low tensile strength and fracture resistance. So, this is a brittle material we are dealing with. So, it fractures fast. So, something which is sick, and this is the problem. The patient comes back with all these issues. So, what are the methods of strengthening? So, there are many techniques, and the first one is developing residual compressive stresses within the material, which will interrupt the crack propagation. So, this is done by reducing the number of cycles and optimally designing the processes. And there is one technique called ion exchange technique, and finally, there is something called thermal tempering. So, each one I'll be dealing in detail in the coming slides. So, what all this finally do? All these techniques do dispersion strengthening and something called transformation strengthening. So, this is like compressive residual stress. When the patient bites into a crown, so many vector forces will result on it, and that can result, if there are some minor flaws within it, that can result in cracking. So, how do you induce residual compressive stresses into the material? So here the coefficient of thermal contraction of metal should be slightly higher than that of porcelain. Metal contracts slightly more than the porcelain on cooling from firing temperature to room temperature. So when metal contracts more, it pulls the ceramic inwards, and this results in compression of porcelain. So this leaves porcelain in residual compression and provides additional strength for the process. So this is one of the techniques. So here it is the contraction that causes the ceramic to pull inwards, thus closing the flaws beneath and not allowing the crack to propagate. So you can see there is a ceramic, the metal ceramic. Metal is the core, and ceramic is the coating which is given outside. So another technique is minimizing the number of firing cycles. So multiple firing. So many a time you fire the same thing, it increases the concentration of the crystalline lucite. So more the firing, the more crystalline growth. If this crystal is called a lucite. So increasing the number of firings increases the lucite content in it of the veneering porcelain. So when the coefficient of thermal expansion exceeds that of metal, a mismatch happens between the metal and between the metal and the porcelain. This mismatch causes stresses on cooling. So tougher and stronger ceramics can sustain higher tensile stresses before crack develop in areas of tensile stress. Well-rounded line angles reduce stresses concentration in restriction. So that is what you want. You don't want any line angles in your tooth prep. So all these should be rounded. If there are any sharp areas, stress will concentrate there. So you have to avoid knife edge margins to avoid risk fracture, cracking or chipping off during firing and also during usage. And using a fine grit abrasive to reduce the probability of forming microcakes and reducing the depth of microfissures produced by these abrasive particles. And next technique is ion exchange or chemical tempering. So this is a very effective method of inducing residual compressive stresses. The sodium containing glass particle is placed in a bath molten potassium nitrate. So what happens then? Then an ion exchange takes place. And what type of ion exchange? So here the sodium ions within the ceramic material is replaced with potassium ions. This potassium ion is 35% larger than the sodium ion. So the areas left by the leached out sodium ions will be occupied with a potassium ion, which is 35% larger than that of the sodium ion that is vacated that space. So what happens? How can it fit into the space? Since it is 35% bigger than the other one, it squeezes into these areas. That squeezing of the potassium into these crevices that cause very large residual compressive stresses within the material. So this potassium-rich slurry is applied to a ceramic surface and is heated at 450 degrees Celsius for 30 minutes for this ion exchange to take place. So gradually all the sodium ions are replaced by bigger potassium ions which squeeze into the position of the previous sodium ions, and this squeezing in causes some residual compressive stresses that in turn strengthen the ceramic. So this is what ion exchange. You can see the sodium ions are leaching out and replaced by potassium ions. So this is another representation. You can see that, the bigger porcelain, the size difference you can see between sodium and potassium. See the size difference. So the bigger one squeeze into place, and that causes some stresses, induce some stresses within the body of the mass, causing it, making it more strong. Now, another technique is thermal tempering. Here, what is done is rapid cooling. So, when the material is in the molten stage, the surface of this material is rapidly cooled using a jet of air. So, what happens? The surface cools and solidifies fast while the core remains molten. And this molten core solidifies, shrinks, and pull the rigid outer surface inwards. So, as I told you, it's a molten mass, and only the superficial surface is cooled by a jet of air. Once that cools down, beneath the whole thing is molten. That slowly cools down. Once it cools down, it shrinks and starts pulling the outer surface inwards. This causes again residual stress. So all these techniques are inducing residual compressive stresses into the material. So this causes another residual compressive stress and thus strengthens the ceramic core. So as already mentioned, a thermal tempering creates residual compressive stresses, and that finally results in strengthening it. So the molten core solidifies slowly, it shrinks, and since outer skin is rigid, it starts pulling. It starts pulling onto it. And as it shrinks, this pulling and this shrinking, this solidification creates the residual compressive stress, making the whole thing quite hard. See, this is a technique, a graphical representation of what I just explained. So again, what are the methods of strengthening? Development of basic technique ideas, developing residual compressive stresses within the mass. So this is achieved by mismatch in coefficient of thermal expansion, COTE, reducing the number of spiral cycles, optimal design without line angles, sharp angles, using techniques like ion exchange and thermal tempering. And finally, what happens is interruption of the crack propagation. So there is dispersion strengthening and transformation toughening happening within the material. So what is dispersion strengthening? So ceramic is reinforced with dispersed paste of a different material. You reinforce them with a dispersed paste of different material that is capable of hindering crack propagation. So what is this hindering material? It can be crystal phases like lucite. It can be metallic things like alumina, zirconia. It can be magnesium steel. So these are the dispersed phases, and when they scatter around, they prevent the crack from propagating. The crack comes and intercepts with these crystal phases, and these crystal phases just prevent further propagation of crack. So that is how it's done. And dispersion strengthening, the Crystalline materials such as alumina is added to a glass and the glass is strengthened and the crack preparation does not take place easily. So that is how dispersion strengthening. You add something like alumina. And a ceramic or a porcelain rich in alumina is known as aluminous porcelain or aluminous ceramic. And dispersion strengthening, it reinforces the dispersed phase. This is achieved by adding filler particles. That this helps in absorbing energy from a crack and prevents crack propagation and interferes with this propagation, thus improves fracture resistance of the ceramic material. So this is how it happens. You can see the filler particles within the matrix. So whenever a crack propagates, it will be stopped by these crystalline silver or crystalline metallic filler particles. Now, another thing is transformation toughening. This method also relies on dispersion of the crystalline material within the ceramic. And the strengthening occurs due to change in the crystal structure under stress, which prevents crack propagation. Transformation toughening, again, continuing with it, dental ceramics based primarily on zirconia crystals when heated at a temperature of the range of 1400 and 2000 degrees undergo change in the basic crystal structure from tetragonal to monoclinic. So this is a very peculiar feature of zirconia. You will learn it in higher classes. The toughening mechanism results from controlled transformation of this metastable tetragonal phase to a stable monoclinic phase. So this is what happens in zirconia, and this will be dealt with at the right time. So now this is for your assignment. What are the methods of strengthening? And in that, please explain the ion exchange technique in few words. So I hope you understood this presentation and you need some additional reading material also. Just by listening to a PowerPoint presentation, you will not get it. So read it. And once you're able to explain something in few words, that means you understood it quite well. So th thank you so much. And thank you for the time given to me. Hope you get the topic and study well.